Molecules, Compounds, and Chemical Equations, Part 6. Today we're going to be talking about limiting reagent problems. So our first question is, what are limiting reagent problems? Then we're going to look at a worked example of a limiting reagent problem, and then we're going to look at one more because repetition here is good. When all the reactants in a chemical reaction are completely consumed, in other words, they're all converted into products, then the reactants are said to be in stoichiometric proportions. On other occasions, it may be necessary to ensure that only one particular reactant is completely used up. This is achieved by using an excess of all the other reactants. The reactant that is completely consumed is called the limiting reagent, and it determines the quantities of products that form. So let's look at an example of a limiting reagent problem. The first thing that we're going to have is a balanced equation. Then we're going to have a word equation associated with that. So 3.04 grams of aluminum reacts with 7.42 grams of iodine to form aluminum iodide. Determine the limiting reagent, the maximum amount of product formed, and the mass of the excess reactant. So the first thing that we're going to do is find the limiting reagent, and that is step 1. Change all of the masses of the reactants into moles. Convert to moles, one of our AP chemistry mantras. So we have two masses here. We have 3.04 grams of aluminum, and we have 7.42 grams of iodine. Don't just put I. Your number of moles will be off, and that's really detrimental. So the first thing that we're going to do here is convert each of these masses into moles. So I'm going to set up a multiplication sign and a line, and I know that there are 27 grams of aluminum in 1 mole of aluminum. I'm going to get an answer for that, and I'm not going to worry about significant figures right now. I'm just going to multiply and divide this through. So if I work that out, I should get 0.11259 moles of aluminum. Then I'm going to do the same thing to iodine here. So multiplication sign and a line. The gram formula mass of I2 is 254 grams of I2, and that is equivalent to 1 mole of I2. So if I do the math for here, I'm going to get 0.0292 moles of I2. So step 1 is converting our given masses of our two reactants into moles. Step 2, divide each reactant's moles by the coefficient from the balanced equation. This is going to determine the limiting reagent. From step 1, I had 0.11259 moles of aluminum, and I had 0.0292 moles of I2. So what I'm going to do here is divide each of these by the coefficient from the balanced equation. So the coefficient in front of the AL is 2. So I'm going to put a 2 here. And if I divide that out, I'm going to get 0.0563. No units. Okay, this is helping us determine the limiting reagent. Do not worry about units. I'm going to now take my moles of I2. The coefficient in front of the I2 is 3. So if I take 0.0292 divided by 3, I'm going to get 0.009737. Now, the limiting reagent is the smaller of these two numbers. So if we look at iodine, we notice that this is a smaller number. So this is my limiting reagent. And I'm going to refer back to this over and over again in this problem. Step 3 is to use the original mass of the limiting reagent and determine the maximum amount of AlI3 produced in grams. Okay, I know that there are shortcuts here, but for the sake of not making mistakes, my suggestion to you is to always go back to your original masses. So the original mass of the limiting reagent, we determined that iodine was our limiting reagent. So there is going to be a little bit of overlap here, but really that's okay. So I'm going to start out with my original mass, which is 7.42 grams of I2. And I'm going to convert that into moles. So I know from my previous example that there is 254 grams of I2 in 1 mole of I2. And now what they ultimately want is the maximum amount of AlI3 in grams. So this second ratio here is going to be a ratio between moles of I2 and moles of AlI3. So if I have I2 on top of here, that's going to go on the bottom of here. So moles of I2, and I want to get to moles of AlI3. And again, I'm going to go back to my balanced equation because this section right here is just a mole-to-mole problem. So I'm going to go back to my balanced equation. I'm going to look at the coefficient in front of I2, which is 3. I'm going to look at the coefficient in front of AlI3, which is 2. And now I'm in moles of AlI3. And maybe some problems will tell you that's where you can stop. But this problem does not. They want this produced in grams. So we're going to do a multiplication sign and a line. And our last step is going to be converting from 1 mole of AlI3 into grams of AlI3, which is 408 grams of AlI3. So if I work this out, and I know I'm on the right track, if I can go through and I can cancel my units, moles of I2, moles of I2, moles of AlI3, moles of AlI3, I'm left with grams of AlI3, which I want in the end. And if I work this out, my mass of AlI3 is 7.946 grams of AlI3. And that is my theoretical mass that could be produced if every single bit of this I2 was used. So from a theoretical view, this is the maximum amount of product that could be produced if all of the limiting reagent was consumed. So the reactant that limits how much AlI3 can be produced is our I2. So if this total mass of iodine was consumed, nothing left over, the mass of AlI3 that could be produced is 7.946 grams. Let's go on to the next step. Determine the amount of the other reactant used during the consumption of the limiting reagent. So we know that I2 is our limiting reagent. That means Al was not. There will be some Al left over, and that's what we're trying to figure out. How much aluminum was actually used in this reaction. This will be done by taking the original amount of the limiting reagent and converting it to the amount of the substance in excess. This amount can either be in terms of moles or grams depending on the question being asked. This is going to be the exact same setup as step 3, except instead of calculating the mass of AlI3, we're going to calculate the mass of Al. So let's get started. We're going to start with our original mass of our limiting reagent, 7.42 grams of I2. And again, I'm sure there's some of you out there going, why is she doing this? She could be taking shortcuts. Well, it's because when I do shortcuts, I make mistakes. And I don't like making mistakes. So I've just converted my original mass of I2 into moles of I2. Now I'm going to go from moles of I2 to moles of aluminum, the other reactant that was not completely consumed. And again, I'm going to use the coefficients from my balanced equation here. So I'm going to put a 2 here and a 3 here. And then my last step here is to convert into grams of aluminum. So I know that in 1 mole of Al, that's going to be 27 grams of Al. And again, before I do my calculation, I'm going to say grams of I2, moles of I2, moles of I2, moles of Al, moles of Al. I'm left with grams of Al, which is what I want. And when I work this out, it's going to be 0.5258 grams of aluminum. Now, what does this represent? This represents the amount of aluminum used in the consumption of all the I2. This is how much was actually consumed compared to the original mass of aluminum present at the beginning of the problem. So the last step is to determine the amount of the reactant that was not consumed by the limiting reagent. The original amount of the substance in excess is subtracted from the amount consumed. The original amount of aluminum that we started with was 3.04 grams of aluminum. We saw in step 4 that 0.5258 grams of aluminum was consumed. So what we need to do here is subtract these two numbers. So if we subtract these two numbers, we're going to get 2.514 grams of aluminum remaining. This is how much aluminum is in excess that was not used as part of this overall chemical reaction and the consumption of this I2. So in this problem, we have figured out the limiting reagent, the theoretical amount of product produced, the amount of the other reactant that was used during the reaction, and the amount of the reactant that was not consumed, how much of that was left over. Let's look at another example. The two nonmetals, sulfur and chlorine, react according to the equation below. If 202 grams of sulfur are allowed to react with 303 grams of Cl2 in the reaction above, which is the limiting reactant, how much product will be produced, and what mass of excess reactant will be left over? So the format of this question will be exactly the same as what we just did. So our first step here is to change all of the masses of the reactants to moles. So I have 202 grams of sulfur, and I have 303 grams of Cl2. And I'm going to say that the atomic mass of sulfur is 32 grams of sulfur in 1 mole of sulfur. And when I work this out, I'm going to get 6.3125 moles of sulfur. And then I'm going to do the exact same thing down here. In 1 mole of Cl2, not just Cl, but Cl2, there's approximately 71 grams of Cl2. And if I work that out, I'm going to get 4.268 moles of Cl2. So that is step 1, taking each of these masses that they're given to you and converting them into moles. The next step is to divide each reactant's moles by the coefficient from the balanced equation. So for sulfur, we had 6.3125 moles of sulfur, and we had 4.268 moles of Cl2. So the coefficient in front of the sulfur is 1, so that's just 1. So that's just going to give us 6.3125. And the coefficient in front of the Cl2 is 3. 3. So if I divide that out, it's going to be 1.422. Now I'm going to look at these two numbers and I'm going to say which one is smaller. And obviously the 1.422 is the smaller one, which means the Cl2 is our limiting reagent. This is what's going to drive how much product is formed. This is the reactant that will be completely consumed. Step 3. Using the original mass of the limiting reagent, determine the maximum amount of SCl6 produced in grams. So I know that my limiting reagent is this Cl2, and my original mass is 303 grams of Cl2. So I'm going to start this by writing my original mass, 303 grams of Cl2, and I'm going to convert this into moles of Cl2. I know that there's approximately 71 grams of Cl2 in 1 mole. Once I'm in moles of Cl2, I can convert this into moles of SCl6. So moles of Cl2 to moles of SCl6. And then I look at my balanced equation and I see that there's a coefficient of 1 in front of the SCl6 and a coefficient of 3 in front of the Cl2. Once I'm in moles of SCl6, I'm going to convert that into mass of SCl6. So I know that 1 mole of SCl6 is equal to approximately 245 grams of SCl6. And I want to go to grams here because they're asking for it in grams. Finally, the last thing that I want to do is check my units. Grams, grams, moles, 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 left with grams. So if I work this out, my theoretical yield is 348 grams of SCl6. Again, this is the maximum amount of product that could be produced if all of my limiting reagent is consumed, all of my Cl2. We also call this theoretical yield. Step 4, determine the amount of the other reactant used during the consumption of the limiting reagent. Remember again, this will be done by taking the original amount of the limiting reagent and converting it to the amount of substance in excess. This amount can either be in terms of moles or grams depending on the question being asked. So I'm going to start with my mass of limiting reagent, which is 303 grams of Cl2. Just like I've done now many times before, I'm going to convert into moles of Cl2, equivalent to 21 grams of Cl2. And instead of going to my product, I'm going to go to my other reactant. So we are converting from moles of Cl2 to moles of sulfur. Going to go up and look at my balanced equation. There is a 3 in front of the Cl2. There is a 1 in front of moles of sulfur. And finally, I'm going to convert that moles of sulfur into grams of sulfur. So 1 mole of sulfur has the atomic mass of approximately 32 grams of sulfur. And I am going to go through and check my units. Grams, grams, moles, 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 left in grams of sulfur. And if I work this out, I'm going to get 45.5 grams of sulfur. And again, this is the amount of sulfur used to consume all of the Cl2. So finally, step 5, to determine the amount of reactant that was not consumed by the limiting reagent, the original amount of the substance in excess is subtracted from the amount consumed. So if we go back to our original statement here, we know that we started with 202 grams of sulfur. This is our original amount. The amount of sulfur consumed during this process was 45.5 grams of sulfur. This is the amount that was actually consumed. If we subtract these two, we have 156.5 grams of sulfur remaining. This is the amount of sulfur in excess. So what did you learn? We talked about what are limiting reagent problems. We did one worked example of a limiting reagent problem. Then we did another worked example of a limiting reagent problem. In reality, that's more than enough. Need more help? Feel free to contact me. Have a great day.